Now that we've prepared our image data, it's time to take what we've learned and use it to build a classical or dense neural network. In this section, there's a lot of material to cover. First, we'll look at classic or dense neural networks and their structure. And then we'll talk about activation functions and nonlinearity. And when we go to actually classify, there's another piece of math, the softmax, and we'll discuss why that matters. After that, we'll look into training and testing data, dropout and flatten, which are new components in networks in order to make them work better, how machine learners actually solve, and then concepts of hyperparameters and grid search in order to fine-tune and build the best neural network you can. Let's get started. In this video, we'll be looking at the actual structure of a classical or dense neural network. We'll start off with a sample neural network structure, and then we'll expand that to build a visualization of the network that you would need in order to understand the MNIST digits. And then finally, we'll relate how the tensor data is actually inserted into a network. Let's start by looking at the structure of a dense neural network. Using the NetworkX package, we're drawing a picture of a neural network, here setting 3 layers, an input layer, an activation layer, and then an output layer, and fully connecting them. That's what these 2 loops in the middle are doing here, are putting an edge between every input and every activation, and then every activation and every output. That's what defines a dense neural network, the full connectivity between all inputs and all activations and all activations and all outputs. And as you can see, it generates a picture that is very densely connected, hence the name. And now let's expand this to 2 dimensions with a 28 by 28 pixel grid that's the input network, followed by a 28 by 28 pixel activation network where the learning will take place, ultimately landing in a 10 position classification network where we'll be predicting the output digits. Now you can see from the dark lines interconnecting, this is a very dense structure. It's so dense in fact that it's actually hard to see the edges of the individual lines. So these lines are where the math will conceptually be taking place inside of the network. Activation functions, which we'll cover here in the next video, are the math that takes place along each one of these lines. And so the relationship between tensors and networks is relatively straightforward. The 2-dimensional grid of inputs, the pixels in the case of this image, are where the 2-dimensional encoded data that we learned about in the previous section will be placed. Inside of the network, math operations, typically a dot product followed by an activation function, are then the lines connecting one layer to another.